Okay, it's 6 o'clock, so I think that we will get started. And first thing is to welcome the members of the public, those who are joining with us today. It is nice to see you. We've had quite a big registration for our talk tonight. Just as a way of introduction, my name is Gary Johnston. I'm the chair of the Armet Scottish Centre and your host for tonight. You probably saw before we just came on live there just now with Nick that there were some screens went up about Armet. I would encourage you, if you're not already a member of Armet, to join Armet. If you have a look at their website, armets.org, a wealth of information and a great organization with lots of benefits. So please do have a look. I would hope that the quality of sound is good tonight. We've changed the software that we use for these talks. So I would hope that everything, the picture quality and the sound is good. If not, I would ask you just to close your browser and log on again and see if that helps. Right, our talk tonight, like all talks, it will be recorded and will be available shortly on YouTube. It is subject to a release being granted by Nick for the talk to become public. Once we start the talk, you will see at the bottom of your screen that there is a Q&A box. And I would ask you if you could, any questions during the talk, if you wouldn't mind putting your questions in there, and we will ask Nick to address these at as many as he can after his talk. If there are any specific slides that you're referring to or you want to have questions about, could you please note either the number of the slide or the name of the slide so we can put it back up on screen, please. So we will move to the talk, and I'm very pleased tonight to introduce Mr. Nick Silkstone from the Met Office. As you know, you'll hopefully have read a bit about Nick, but Nick has worked at the UK Met Office in various operational meteorology since 2008. In that time, he's worked widely across the UK and overseas, including places such as Antarctica and St. Helena Island. He currently works as Deputy Chief Operational Meteorologist in the Met Office, Exeter HQ, covering roles such as the UK Medium Range, which is +2 days, Global Guidance Unit, covering UK interests overseas. And in recent years, has been heavily involved in Nowcasting, Meso-Analysis initiative. This project has been targeted to improving very short range 0 to 6 hours forecasting of summertime showers and thunderstorms. So Nick, over to you. Thank you.
Thank you very much, Gary. It's much appreciated. Good evening, everyone. I will just get my screen shared and yeah. And hopefully, I don't know if anyone can let me know if you can see that, Gary. Is that there for you? Can you see a presentation?
We're just getting a blank screen at the moment, Nick. Just black.
A blank screen. Let's have a look.
There we go. Yeah, that's it. Thank you.
Excellent. Great stuff then. Right. Thanks very much. I'll get going again. So yeah, this will be a talk lasting about 45 minutes on the Nowcasting project at the Met Office, as Gary has introduced really well. You'll be thankful to hear I'll skip over and be quite short with some of the the project sides of it and tend to focus on bits of the meteorology and little bits of the work that we've done towards that. It'll be dotted with lots of imagery, tools that we've developed to show you. So yeah, hopefully it will be of interest and I'll be happy to, as always, take questions at the end of the show. So I'm just going to start off then. These are the sections that I'll be running through tonight. You can read them down the left-hand side. Some of them will be quite quick and short, but basically just giving you technical terms, background, running through the project as it is now, looking then very briefly at the future plans before I move on to questions at the end. So we'll start then. What do the technical terms mean? So Gary's always introduced it well. Nowcasting, a couple of definitions that I quite like there. There's the one from the World Meteorological Organization, and then the one that they based that on from Keith Browning, who was at Reading several years ago. And that's the one that I quite like, certainly when it comes to the human sort of element of nowcasting, what we're trying to do as Meso-Analysis, and that's the description of the current state of the weather in detail and the prediction of changes that can be expected on a time scale of a few hours. So we're effectively doing a lot of very detailed analysis of the present and using that to extrapolate some key things in the future where, you know, in this case, where showers and thunderstorms are likely to form, decay, and other features such as that. So Meso-Analyst, or Meso-Analysis, and the Meso-Analyst role, which we've created to do this, is something that's probably quite unique as a term to meteorology. So in meteorology, we've got a whole host of scales that are quite different. And I've just listed a few of them you can see on the right hand side there. So synoptic scale, I've shown you with a satellite picture, we're often talking over thousands of kilometers. Things on the synoptic scale are large scale features such as low pressure systems, high pressure systems, you know, they cover often countries or more. The meso scale is as it says down at the bottom there, on the scale of sort of 10 to 100 kilometers. So we're looking very much at smaller regions, features such as where there's sea breeze fronts, convergence lines, heating over topography, what we call cold pools, outflows from previous showers. And it's the clues when looking on that meso scale and doing that very detailed analysis, which give us those clues to, you know, how a shower is likely to behave or thunderstorm, and its sort of variations. There are a whole host of smaller scales than that, say storm scale, micro scale, and it just goes on and on. But that's where the word meso comes from. If anyone's interested, it's just about the scale. So a bit of background to the project then, and how we got to this place in the Met Office. So in the 1980s and 1990s, and even stretched into the early 2000s, the Met Office's main ways that we had difficulties, or, you know, I wouldn't say got into trouble, but, you know, our performance was lacked, has been poor, was with some of the pretty significant winter windstorms. Definitely the 1987 one bears, you know, well in the memory of many people, and for yourself, things such as the Burnsday storm and say other events through that time. This resulted basically in the development of our tools, training, NWP, and even our people to focus on the forecasting of synoptic scale systems. And those main hazards that are associated with those, such as, you know, strong winds, the heavy rainfall, and then the other various bits in winter. I should say as well that during much of this time period, when you're trying to do analysis on the meso scale, you're requiring a really fine density of observations, really granular radar data, satellite data, and much of that as well didn't really exist, you know, before we got into the mid part of the 2000s decade. For example, I've got our observing network, our official observing network there, as was in 2010 when I took that screenshot. And if I just show you, for example, across Lincolnshire, let's see, in and around, you probably can't see my pointer, apologies there. In and around Lincolnshire, you can see that we've only got around about 5 observations across the whole county. So when you're trying to track something such as a sea breeze front, you may see it come onto the coast where we've got a couple of range sites, but until it reaches the RAF stations on the Lincoln Ridge, which is, you know, of the order of sort of 30, 40 kilometers, yeah, there's nothing to show. So it was almost preventative of us doing that. Some things that started then, as we moved beyond that into later years, we started to get much improved observations. The WOW network, if anyone uploads their weather station data, that it's much appreciated, and it really does actually have a pretty key role in this project. We also had the launch of Meteosat second generation, which provided much greater satellite imagery from a geostationary orbit. Things such as our radar, where the resolution reduced from, when I joined the Met Office, individual pixels were 5 by 5 kilometers, which is quite some size when you're looking for details within a shower and trends, down to radar now, which is around about 500 meters coverage that we've got across much of the UK landmass. So in addition to having the tools, the observations to actually perform meso analysis in an adequate way, which we've gained over the last sort of 15 years or so, we've also had multiple sort of significant summertime surface water flooding events. So we may all remember back to Boscastle in Cornwall 2004. We've had various events then through London, Birmingham in recent years. And the one that sort of kicked this initiative off, once again, I've got some gravitas behind it, was the events at Cumulatives in Cornwall in July 2017. I was actually working this day, not covering that part of the country, on an aviation bench at the time. And I remember being in operations centre. There was actually disagreements, or not quite arguments, but people were not convinced that the shower that was impacting Cumulatives before we got the reports, I should say, of the flooding was actually even reaching the ground, which is quite staggering. And there were a whole load of reasons for that. On that day, the showers were coming mostly from medium level or elevated convection. That means the base of the clouds are a long way above the surface. On that day, I believe it was mostly around 10 to 12,000 feet. And the radar had been performing quite poorly across southwest England. For example, we were supposed to have had showers of quite significance over our Exeter headquarters where we all were. But we'd only witnessed, a few big spots of rain, landing on our windows and the roof. So there was question marks about radar performance in southwest England on that day. The long story short is that everything existed in the Met Office, all the data for us to know that rainfall was reaching the surface, to know it was definitively heavy rainfall, not wetted hail, which is very reflective and can con you when looking in the composites are thinking there were hideously high rainfall rates, but the data was hidden away, difficult to access. People were not overly well trained on how to utilize that, so it meant that it was just missed. So on the back of all that, we got the data, we've had a few events, and we then had the impetus to start looking into, could we start conducting detailed meso-analysis? Could we start upskilling people and work on this going forwards? Another thing that helped push this project into starting was in sort of 2018, the Public Weather Service Customer Group, who are like an independent sort of body who are owned by BASE, who are a sort of owning government department. I should say there's some information on those and the link at the bottom of the screen. It includes people from the devolved administrations, from the emergency services, MOD, other people like that, and they make up a body that helps steer the direction of the Met Office's Public Weather Service offering. And they'd requested that we introduce thunderstorm and lightning warnings to the portfolio. And with the first one you can see there going out on the 1st of July 2018. I just thought I'd give you an insight to NSWWS, or National Severe Weather Warning Service verification score. So these are approximate, they vary month to month as events drop in and drop out. But we average these across a 36-month rolling period. These are the two scores that I put here. There are other ones there, misses, for example, but I've just highlighted here ones that we get scored good or excellent guidance on, or poor or very poor. And I should say that warnings that are only judged to have reached an amber level or above are actually assessed. When we look at all hazards, this includes, wind, rainfall, snowfall, all NSWWS, we tend to get around 80 to 85%. That's roughly where we sit for our warnings assessed as good or excellent guidance, and only 5 to 10% in the poor or very poor guidance space. But in the last 3 years, if you separate out, say, warnings related to showers, thunderstorms, often these are in the form of surface water flooding, you can see that the statistics are significantly poorer, with the good or excellent guidance generally being at less than half of the events that are assessed. So that also highlighted to us, this is going to be something that's more visible coming forwards. We've got a significant weakness in there, partly because they're just hard, they're small scale, there's some almost randomness to this, but we thought there was a potential there through developing this capability to make some pretty significant gains and help contribute to the overall scores. So this was the project goal and its objectives as set up in, I believe this is 2018, 2019, this was penned down. So ultimately the goal of the Nowcasting project is to identify and communicate potential hazards with improved lead time and specificity, terrible with that word, to drive downstream decision making with a focus on hazards that present a safety to life. So there are a lot of things that do that, but as I say, with that weakness being on warm season showers and thunderstorms, I say warm season because when the air is warmer, it can hold more moisture, and that sort of ups the ceiling of the amount of water that can fall, and that's when we tend to get most of our significant surface water or flash flooding issues. So that was our initial focus: summertimes, showers, thunderstorms, particularly those that are developing surface water flooding. I should say that my part of the project that I worked on was very much about developing the capability, so the ability to do this, the ability to identify these things, to offer this advanced guidance. And we didn't really, certainly during the trial phases of this project, start thinking about the service or the end product that would make it through to the customers. We were just working out, could we do it? Did it work at that stage? There's a graphic on the right side that shows basically how we tried to sort of make this a all-encompassing circle of a project, from training, data, process, and alerting. At the moment or before this, we relied on human eyes to basically pick up most things that were happening, rather than anything sort of popping up to say we've seen X or Y here. And then through the analysis, interpretation, production, and dissemination, delivery, and then complete the circle to make it holistic. So we're constantly learning from events, we're constantly improving. and making things easier on the humans in the loop. And I should say that before this project, much of our sort of, certainly on the operational side, the Met Office was stuck between 4 and 6, and we did very little or far less than we should have of the areas 7 through to 3. So we were also trying to sort of more holistically join up the back end as well as the things that we do on the observational side with this. So I'll next go into some of the developments then that have been put together in recent years as part of this to help us, you know, basically assess what's happening at the surface, assess what's happening in places, to make better judgments upon it. So I'll start with developments that our science team that have been spun up put in, and the first one is something called the gridded Meso-Analysis. So this is a really clever piece of kit. It was initially developed by Matthew Clark, who did it as a gridded format, and that work's been taken on by another chap called Ed Pavlin in the Met Office. So how this works is that our official observation sites, official observations are still very sparse. You know, observations are often separated out, you know, tens of kilometers apart. They don't sample everywhere overly well. We know they're high quality, but say not dense enough. However, in the last 10 years or so, the WOW, or Weather Observations website that the Met Office has run, has seen hundreds, if not thousands, across the UK of enthusiasts uploading their automated weather data to it. That data is of varying quality, you know, some high, some low. I know the exposure of my own station that uploads is less than optimal, certainly when it comes to the height of my wind mast. But we're able to basically use the official observations, knowing that those WOW-OBS sit in place, to apply some quite clever bias correcting to their local observations, and basically allow us to have a much denser observation network as a sense which is in some senses corrected to it. It's also quite clever in that it takes things like something called ensemble optimal interpolation on NWP fields, and it effectively means that every observation has got a radius of influence, and it shares that with observations around it. And it's quite clever. Parameters are shared. So we know, for example, that in people's back gardens, they're unlikely to get, you know, good, reliable measurements of wind speed. You know, they're close to houses where it filters funnels, you know, you get turbulence, bits and pieces like that. But other things are much more accurate. So, for example, temperature tends to be pretty good. You know, if you've got good exposure and not got your thermometer sat out in the sunshine, and pressure, which is one of the more simple things to measure. But it's quite clever. Pressure actually influences wind. So, for some of these observations, for example, sit lower than the models means sea level pressure, they will actually nudge it. So they will change the pressure, and then all other fields in this Meso-analysis, so wind, for example, will change on the influence of that. So we'll get stronger winds. It will basically balance and adjust as you would see in the real atmosphere. So basically the crux of this is that we get a really highly detailed analysis of the current atmosphere from surface observations that is heavily influenced by the observations, not the background model. And as a human, this is great that it's gridded. We can see things, it's shaded, it draws the eye. As prior to this, we were basically hunting through these individual observations themselves, trying to find, you know, things like, you know, where the sea breeze had gone through, looking where the temperature had dropped, and you know, perhaps a little bounce in pressure. So yeah, just once again, a massive thank you to everyone who's uploaded to WOW. It really does help. There are some problems with it. So evidently urban areas have much better coverage where there are many more weather stations than rural ones, and particularly some parts of, you know, the Highlands of Scotland and remote areas, it becomes somewhat more of a challenge. But I just thought I'd show you a few fields here that were developed that were as output during the flooding event in parts of Western Fife and Perth on the 8th of September this year. So this one on the left-hand side is using basically surface temperature and dew point to assess surface-based convective available potential energy. So this is the total value, and you can see it's shaded by the number of joules per kilogram. Basically, the lighter the color, the more potential energy there is to be, you know, ingested into a thunderstorm or shower updraft and produce that. And then on this lower side is the increment. So this is the difference that the observations have made to the model's background. I'm just going to say on this event, we had basically a line of thunderstorms and showers following this black line that was moving towards the northwest. And they were basically forming just on the offshore portion of here, just off, I forget all the first, the third and fourth in here. The low level wind was from the northeast, and you could see that on this northeastern side, if I should show you the other fields, the temperatures were warmer than model expectations. It was, you know, the cloud had cleared, and that resulted in there being more surface-based convective available potential energy. And that was shown as this increment here. You can see these shades of pink are indicating that Kate value was increased of the order of, you know, 1 to 300 joules per kilogram above the model background field. And that was basically feeding into this line of showers that were forming in this region before they matured and pushed westwards across parts of, say, Western Fife and Perth, which brought a very specific and small area of surface water flooding. So next then we've got 3D radar. So this is brilliant. Most people see radar, they just have what we call the radar composite. And that's effectively our best guess at how much rain is hitting the surface and where. So that's there to feed things such as our app, for percentage of precipitation, and just for people who are looking at it to give them their very much best estimate. But there's so much more to radar data than that. We don't just, scan at the bottom edge of the atmosphere. The radar beams are actually directed up in a whole host of degree angles that get steeper and steeper. When we overlap these together and put them in something called a 3D radar cube, we basically can have a reflectivity profile in 3D of the entire radar sphere. And then from that, there's a whole host of diagnostics, I must say, that we've borrowed from the United States, where they were mostly developed, that can allow us to basically assess cells. So here, for example, we've got cross sections which look at basically the reflectivity through height. This is on the east-west. So through here, I'm seeing this cells, and likewise in the north-south. And these are zoomable, move around about maps and other bits and pieces. This is fantastic because it means that we can see basically where updrafts are strengthening, where hydrometeors have been lofted higher into the convective clouds, where they're weakening, where they're basically falling down. The high reflectivity are becoming down to lower elevations, and allows us to do a whole host of clever things, I say, from those techniques from the United States on them. So it allows us to produce these cross sections. It allows us to look at lightning diagnostics in the next 30 minutes. That was developed by KNMI, which is the Netherlands Met Service, and a whole host of hail diagnostics as well that are hugely interesting. In addition to that, on the 3D radar, it's allowed us to track cells much better as they go through their various phases. So we've got automated cell tracking now. Here it is, it's actually shown by these various little red and black lines where the cells have been in the past and where they're identified as being at the present time, I should say, in red. This is brilliant. It means that if we can track a cell, it's not just in one place. We can actually click on this. You get a whole range of metrics and statistics telling you how it's changing and how its characteristics are, its probability of hail, and all these other things as it moves forwards and backwards in time. And in addition to that, we've got an interpolation technique, which allows us to do some very short-term, you can see forecasts of the cell motion, as it would be with an uncertainty, I should say, that is quite large at the present time. And here I show a 30-minute forecast of the location of these various cells. So a great bit of work, again, developed in-house. Another one that's quite small and probably, see my people, is our actual unified model, certainly for humans, didn't actually produce convective diagnostics up until about 12 months ago. We've developed these alongside basically the European standard recommendations, which allow us to compare them and contrast them with other centres, such as the European Centre for Medium Range Weather Forecasting, and hopefully they'll be adopted more widely across Europe, as there are so many ways to calculate CAPE-STIN and other bits and pieces. But these are brilliant. They do more than just giving you raw numbers themselves. For example, we're able to look at through these what we call the lifting condensation level, or level of free convection. So that's basically the height of a cloud base, the height that a parcel of air becomes buoyant, and even the equilibrium level, which is a reasonable proxy for the approximate height of where the updraft will be. So these have been a real game changer, available worldwide, as well as for our high resolution UK models, and also across the ensemble as well. And these are partly what you saw the Meso-Analyst previously was based upon. Excellent. So as well as there are other science tools that have been developed, but I thought they were the main ones worth showing today. So I'll take you into then when we started this, and it was pretty piecemeal back in 2019. We had basically one person available each day, and we had cleared out a little bit of time moving some tasks on one other shift. We're juggling them around to allow a person to spend the time 10 o'clock till 15:30, so about 5.5 hours per day, to basically look at convection across the UK on that day and the days following, just seeing basically, could we put together any greater insights? Could we find the weaknesses where we had knowledge gaps, and how would this advice, initially be interpreted by people internally? So as I say there in the italics, it was aimed at finding the problems and the shortcomings to address during what we call the proper trial phases, which were the alpha and beta trials, which followed during the couple of summers. And on the back of that as well, we had a modest development budget during that time. So that was really helpful to help us shape some of the things that we wanted to help in those following years. So these are some of the initial products, say very simple piecemeal. I put this one together myself in 2019 on PowerPoint, which is the basic background map. But it did have some initial things. So this was the day where we had an area of low pressure, unstable down towards the southwest, with slow moving showers rotating around it. But further to the northeast, there was basically what we call greater vertical wind shear here, which allowed more severe or more organized modes of convection to develop. And we were able to basically highlight that. This is like written on the 29th, a day ahead, talking about thunder and hail possible. So if you look at this time, this was produced at 12 Zulu's the same time as UTC. So in summer, that's like 1300 local, or 1 p.m. in the afternoon. And this, even in 2019, on some events, we were able to show some helpful. So some early insights, made some small positive doses on some cases. So this was one where there's the warning that was in place on the morning of the 29th before we conducted that analysis. That, along with other things into the 30th, allowed the warning to be extended northeastwards into parts of Yorkshire, and also basically highlighted the potential for hail in that, knowing that there's that potential for more severe and organised convection across this part of the world, which we were able to highlight being over northern England. And on that day, we did actually have several supercells convection which trained across a similar area in parts of North Yorkshire and produced some significant flooding in parts of Swaledale and Wensleydale that even knocked out one of the famous, I think it's the Grinstead Moor Bridge that was used on the Tour de France, was completely washed away along with that. In 2019 as well, during the trials, we started, as part of learning, improving, to develop case studies for events. We initially targeted them at ones that went badly wrong, and it was really useful. It highlighted, gaps in our knowledge and that of the team, some difficulties in accessing and interpreting data. Again, all looking towards improving things once we move into the alpha and beta stages. So this is for the same event you saw previously, where we had, say, this selection of supercell thunderstorms that started to form across North Yorkshire during the early afternoon, trailing all the way down here, which we were able to identify. This is just a slide from the case study, the various things that produced that. And on the next slide, I'll show you some of the difficulties with accessing and interpreting data. So you may have heard of Doppler radar. So Doppler radar basically looks at almost like a phase shift. So it can measure velocities if you've got a target. So we need basically a hydrometeor, which is rain, hail, snow. And if it can strike that, it can basically measure the phase shift, whether that's moving away from the radar along a radial or towards the radar. So it's quite difficult to interpret. Each radar is specific, and there's a whole host of things like that. But it is good for one thing, which is finding what we call mesocyclones, or persistent rotating updrafts, which are a signature of supercell thunderstorms. And also, when you've got supercell thunderstorms, that opens the door to hail and other hazards here. So this is how we access the Doppler data back in 2019. So it was done through an internal Met Office webpage, which was built basically only as a monitoring tool for the radar and observations team, not for access to operational meteorologists. So as a result, the data was as flat .png images. So, for example, when I'm trying to work out what is the strength of this couplet in this region here, I'd be copying and pasting this raw image into Microsoft Paint. I'd be zooming in using the color picker tool to look at how, the darkest color I could find in this part and this part. Then I'd be drawing basically up and down the legend to see where that color matched and approximating the strength on that one. You can also see problems that, there's very little or limited background mapping available. So you're almost guessing the location when you're looking at this, and its ability to overlay different fields, for example, rainfall rate on the Doppler or velocity data, was very difficult to interpret as well. So it just shows you, although this has existed since we updated our radar networks in the mid-2010s, so I think around the order of sort of 2015 to 2017, I think it was completed. There wasn't the tools to get it into our primary visualization systems to allow us to visualize it on a map with other data and do very simple sort of calculations on it. How strong is a mesocyclone? So I'd say on the back of that then, we had a winter development thinking about how we were going to put together an alpha trial during the summer of 2020. So again, we ran this from the 15th of June through to the 2nd of October. And we did it this time rather than just borrowing some time on another bench. So that's quite difficult. Someone was having to split their time effectively by doing some work globally, I think for the Falklands, as well as doing this. So that was feedback that it didn't work well. But we established an on-call roster with coverage, possibly between 6 a.m. and 10 o'clock each day. However, it was only rostered to one person for 7 days, and they only had a maximum of 37 hours per week that they could work. And as we were to find out during the alpha trial, when you have events of deep convection, impactful showers and thunderstorms, they often come in clusters of many days together rather than spread out. So we found as part of the alpha trial that we often exhausted the resource quite early in the week, and it required quite clever or careful planning to make the most of it. The other problem at this point was that among a broad team of people who do a whole host of roles, a deputy chief level in the guidance unit, we effectively shared this between them. So there's 15 people. You can probably look in there at the length of the season, work out that that really wasn't much more than 15 weeks long in total. And with only one person being on call at a time, it meant that we only had basically, most people only visited this bench once per year or once in that season. Of course, that's no good for continuity because you're learning, getting your feet at the table in that first week. And, you know, for many people, the year went by without them seeing a hint of severe convection and being called in to deal with it at all. I should say that through that season, we started producing some internal products to look at, identifying areas of severe convection, various bits and pieces, which we released, and we iteratively improved them based on feedback through the year. On the back of that, training packages, assessments, and then we started, although we didn't have good access, we started thinking of ways we could access the data so much better. So this was an early, what we call meso-scale discussion for some thunderstorms across the southeast of England on the 17th of June 2020, which is how we started on the season. It was quite an interesting one. So we were posting these on an internal, basically Microsoft Teams thing, which is like an internal chat that all of our operational meteorologists, our civil continuity fighters, and others could pick up on. But you can see the problem here. We'd end up basically on most days having multiple meso-scale discussions, multiple small scale areas, numbering them all synchronous with chronology. And that meant that if you had 4 areas you were looking at, you were updating these every 2 to 3 hours. Quite quickly, you ended up with 12, 15 plus of these in a day. And it was possible to find the one you wanted, work out which one was last, and all the other bits and pieces. And it was also found that some of the information in this was a little bit technical. So through the season, we evolved that. And you can see we ended up with this almost all-encompassing UK sort of document, which was a short-term outlook, looking 3 hours ahead, talking about areas of showers that interest us and for what reasons, whether they had a trend of maintaining intensity, increasing with the upwards arrow, or decaying. And we just basically put in here insights for operational meteorologists and for people to take in to learn from this and then pass on to their customers directly. I've already mentioned it so far, before, about the utilization. So this is basically summer 2020 when the trial started in June. These are days that we had yellow or higher impact yellow thunderstorm warnings out, and amber, as you can see here. And the days that the Meso-Analyst or Nowcasting resource was in is boxed in black. And you can see the basic problem was that we had one person on call, Friday to Saturday, 37 hours of resource in that time. But all of the events in that season tended to come, the more significant ones in clumps of days at a time. For example, here we had one that ran, so I'm just counting up in mind, 9 days in total where we required resource and had warnings every day. So that indicates us that resourcing model was pretty much inadequate. So once we got through 2020, then we moved into 2021. One of our key things for this trial, actually, I'll say that in a second, sorry. Actually, the trial was lengthened. We started in April this year, ran it through to October. We still had an on-call roster in place with the same hours, the same limitations of 37 per week, but we now recruited a more specialist team of 6 people, and with one person on call still for 7 days at a time. And we started to develop a piece of software called Visual Weather 6 with a company called IBL. We use Visual Weather, but a much earlier version of this for most operational services. And within it, we produced something called a content creation tool. So this, for the first time, allowed us to, within our piece of software, I've got a screenshot of it here, have meteorological data in the background. We were able to rapidly draw shapes on top of the raw data, add in metadata for these. So I've not actually got a screenshot of it here, but for example, we had start time, end time, validity, what to expect, potential hazards and all that. And literally pressing this little save button here, once saved it, twice sent it. And that basically sent some machine readable content that just pinged straight out and was available for opmets to pick up off a website. I should say that this data as well, this software as well, Visual Weather 6, actually connected to the Amazon, or the server behind it connected to Amazon Web Services, which is where the Met Office has chosen to upload all of our model data. And it's quite a story about this. So the weather industry now, there is so much data that we are almost sinking in it. It's almost impossible to deal with the amount of NWP, especially, that is thrown out from the model day to day. And building, internal servers to do that is costly, humongous, keep them in. So we chose basically to push all our data with a partnership that we had with Amazon Web Services up to the AWS cloud, as we called it. It's free to upload your data to Amazon, but then people pay to download it. So our clients, Met Office people who want data from the Met Office, extract it from Amazon Web Services. That's where they point to. And likewise, at the moment, and it's going to change in the future, operational meteorologists also compete and download that data from the same location as the pools of customers do. But there's quite an interesting facet to that. We get data at the moment in a very raw basic form, which means it is humongous file sizes. And as a result, the costs of downloading data, if you provided all of this, all the ensemble models, everything to every operational meteorologist, would be prohibitively large. You know, we're talking data costs that run into the tens, if not hundreds of thousands, if everyone was hitting this server and downloading it through the year. So this this Visual Weather 6 and all the access to the NWP data was limited to a small subset of one server, which was for the guidance unit, the team that I worked in, and only 3 laptops that could connect to that. But I just thought it's an incredible story that we generating all this data in-house, and at the moment we actually push it out to a place that can store it, but then we can't actually afford en masse to bring it all back. I should say that is going to be addressed in the near future. We're developing our next visualization software at the present time. That's going to see basically most of the data and the crunching of the data done in the AWS cloud. And then when we request it, we're going to be requesting basically things like WMS layers, which are much smaller in file size, which make that a much more viable model going forwards. So back to the content creation tool. Produce GeoJSON objects, which are machine readable, metadata, meteorological data, fully machine readable with them, and that basically output onto various websites. So this is an example. This is a website that we built. This is a pan zoom map. You can add on layers, satellite, radar, everything you wish. And this is how a Nowcasting object was published. So I basically draw this polygon around an area of interest. I then write, you know, the validity times of it, look into the future, the headline, further details and what to expect. It would have a unique ID. And this map, it could have multiple objects on it. You click the one you want, you get the metadata for it left-hand side, you pan and zoom elsewhere, click and you will see it. And it allowed people to basically also create something which is almost like a quick, easy, dirty product that they can pass out or share with the customer. For example, the Environment Agency, you know, it could be passed on to SEPA, in the Scottish Environment Section Agency, among others. And it was a really good tool. It allowed us to basically produce this quickly, easily, in our primary visualization software and get that data out to the masses. So it took 2 seconds from sending it to appearing on this page. And this was a real step forward, not just in Nowcasting, but machine readable guidance, creating content that can be reused, recycled and read is the way forward. And this was a really good prototype that I think will span way more than the Nowcasting project in the Met Office going forwards. So during the, which year we're in, during the beta trial then, we were able to have some real good successes. I should say not every event is completely straightforward. If the convection or the showers and thunderstorms are tied to features that are at the surface, so sea breeze fronts, convergence lines, topography, it's often a much easier subject to get ahead of, to have some insights on and to deal with, compared to if it's elevated convection. So that's where it's happening in layers above the surface where they're sampled much more poorly. So, you know, you only get so many aircraft that fly through these layers, only a few weather balloons per day. And often, for example, they're, you know, over parts like the English Channel or North Sea before they move onshore, such as the events at Perth, which was a mixture of initially elevated, but then some surface-based convection later there. So this was one event where we had some real success. So this was a Nowcasting object that was issued. This purple polygon is highlighted here to the north. That ran from parts of Norfolk and Suffolk down towards Greater London, particularly the central and eastern parts of it. This was issued at 12:30 on the Sunday, the 21st of June, 2021. Talked about basically some really high rainfall accumulations, 60 to 80 mils in a few hours. And it said the risk is, with the risk of the highest accumulations in the southern part of the highlighted area, which is basically in and down here. But if you see the time of this, we were able to issue that at 12:30. When it comes to actually sort of issuing the warning beyond that, I say 12:30 was before even any showers formed upon this line as well. When it comes to issuing the amber warning, because these are assessed, you know, we've got targets to meet, it requires a much higher level of confidence to be able to go from a broad yellow thunderstorm warning, which we had out on this day, to highlight a smaller area of amber. You can see that that wasn't issued until 15:30 BST. So it's 2, you know, even 3 hours later than we were initially able to offer some advice on this region to target the southern part of it, compared to when we're able to get out an amber warning to cover it. And it just showed the promises on some events that looking ahead, look at these small scale features, conducting Meso-Analyst, we do have the skill to highlight areas of interest much smaller than we've traditionally done with National Severe Weather Warning Services at a lead time of several hours, which was a real positive step. So during the beta trial, again, this is a diagram of how the season ran out when we used the Meso-Analyst resource, the various warnings for heavy rain, thunderstorm, and lightnings that were issued on that day. And you can see here that again, it was basically highlighted to us that these tend to happen in clumps of days together, which with 37 hours a week meant we exhausted it. And particularly this period, you can see here around late July, where we had many days in a row, we would have ideally had a Meso-Analyst in for any of these, but because we were having to ration resource and hit them at these amber warning days, the 25th, 27th, 28th, you can see that we actually had days where we had to gap it in between just to cover it. And I should say that as well as doing some of the things when things are escalating, we're able to pick up and provide insights when things are likely to be on the down. So this is the same event which was across surface water flooding across London on the 21st of July 2021. And here basically the Meso-Analyst were able to identify the outflow boundary for the showers, which is basically the cold rain, cold air, which was now spreading southeastwards from the convection. And that was effectively moving and undercutting, moving away from the updrafts, the warm and stable air, which was tied just inland from the coast. I say, well, not on the initial coast because it was a little cool from the sea impact, but just inland, we're getting temperature of 20, 21. And we're able to use this insights to say why the event was likely to end, why the risk was decaying for London, almost giving like an all clear or an improving message, and also show that basically where they were most likely to maintain was the northeastern end of this arc for various reasons about the outflow here. And I think this was one of the ones that produced one of the highest sort of rainfall of this area, rainfall accumulations across the UK, and some work that Dan Holly did and published or was talked about, I think, with the AMATS as well. So moving on next then, this year we moved into the operational service starting on the 1st of April. So taking everything we've learned from the trials, which we wrote up, we had multiple case studies, lots of training, development of the team, improvement and testing of the tools. And it finally got us to this place where on the 1st of April, we put together a service that was able to go live. So this summer, we covered the 1st of April, we're still covering now, I should say, for the 31st of October. We still have an on-call roster. It's slightly lengthened now between 6 and 23:30, but how we've rostered it, 6 people, 3 mornings, 3 evenings pattern, 9-hour shift with half an hour overlap. We're now able to cover it with no limits on resource, because if everyone was called in for every shift that was rostered, they still wouldn't exceed their hours balance per week. The one difference this year, though, was on the back of these developments what the Public Weather Services funded, there was a requirement for us to now start communicating information that is supplementary to NSWWS to the responders and public. So responders are like blue light services, they're sort of the highest category through to sort of power company things, and the public simultaneously. This was really difficult, so it's challenging to get developments done quickly. With big pieces of software, for example, NSWWS Hazard Manager, which is how we distribute, I should say, national severe weather warnings, particularly to the responder community. And we were unable basically over the winter to achieve that in the time. So to meet this remit, which was put upon us of communicating supplementary information to the responders and public, we had to utilize, I've written regional twice, but regional Twitter feeds for this purpose this year, which we all agree was a less than ideal solution, like a really less than ideal, but the only way we were able to get that through. This has got some pitfalls in itself. So the Met Office Scotland feed, being a whole country, has got a pretty good following, 55.4 thousand followers. That compares to the Met Office's main channel, which is around just below 1 million followers, I believe, on the Met Office's main Twitter feed. And that is quite unique and quite high compared to most others. So for example, this is the Met Office Twitter feed for Eastern England that we're able to use. And it doesn't even have a measly total of 5,000 followers at the present time. But I should say where there was real importance and impact, we were able to utilize the main Twitter feed to take these tweets, retweet them, and gain greater reach when events were more severe and warranted that broadcast at a national level. So this is an example of sort of the difficulty that we have at the moment. So the National Severe Weather Warning Service, it was set up, as you know, in response to those windstorms in the late 1980s and early 1990s, and it's evolved in various ways, but effectively it's an advisory service. It's looking to advise people of severe weather, allowing them to take actions, mostly on the scale of, days ahead. So for example, when we've got a significant windstorm forecast, you'll see, the warnings out well ahead of time. That allows power companies, to adjust their manning, people to prepare to do repairs to power lines, emergency services, and bits and pieces like that. So it works really well for things like there are big events like windstorms, snow to some degree, because any amount of snow causes some impact, and rainfall as well, which is closely linked to the rivers. But when you start to talk about showers, the hit and miss nature of them means that it's really difficult to, because often on a showery day, the showers across the whole UK, there'll often be thunderstorms everywhere. And when you're certainly working on the lead time as NSWWS, it's really hard to enter any details. So this is not untypical of what we got. So this is an event on the 16th of August, 2022, when we had a broad yellow NSWWS warning out. So you can see here, it's most people don't know there's a matrix, but there's a matrix that sits behind the colours. So we had medium impacts, which are all very much defined and tie into basically these what to expect impacts. These will change dependent off whether extreme warning, so low, medium, high, and the warning type. And we had basically a low likelihood, which we think is, of the order of 30 to 50%. This is our best practice guide, probability of that event occurring. So here, though, the warning is valid for the whole day, because, we're going to see thunderstorms bringing torrential rain disruption that are moving around. It's going to be different areas affected during different parts of the day. That covers the whole of England and Wales. So we've got 59 million people with a warning valid for the entire day. And we know that probably like 59.99 million of those people are unlikely to see any impacts from this event. And we've had feedback that people feel that when we give this sort of advice, it basically just, we're leaving responders and the public to it, saying, we've said there'll be a thunderstorm. We leave people to radar watch and basically almost work it out for themselves. And it's really difficult, because without that confidence to go in amber, which we only have to do for very small areas, and they're assessed, so we have to see impacts. If we do that, we just basically get stuck in this space where we've got broad yellow warnings and we're unable to offer additional advice at shorter lead time in our current national severe weather warning setup. So on this day in particular, I'll take you through, these are some of the things. So you can see the products now. These are internal updates, latest thoughts and watch points from my colleague, Matthew Leonard, which was posted just after 3:30 in the afternoon, again, Zulu time, which is UTC. So these are internal updates. They go to the Met Office meteorologist teams. They use it to inform customers and pass things on. The Flood Forecast Centre, which deal with the Environment Agency in National Wales, and can be shared via our office in Aberdeen with SEPA as well. Available at a few hours lead time, highlights areas of much more specific interest. So here you can see we've got this whole broad yellow warning out for the whole of England and Wales. But at this point in the coming hours, we're able to tie it down to areas of concern. You see we've got this portion on this convergence line across South Wales, a couple of areas in Southwest England, and then this main area where the greatest totals are highlighted, 70 to 80 millimetres, parts of the East Midlands and Lincolnshire. So we basically had a weak cold front, this blue dotted line moving southwards, the convergence line extending northeastwards, and upper air features meant then this was the pocket where instability was likely to fire. Showers were likely to be, relatively slow moving, and it was basically our hotspot in the coming hours for where we were likely to see impacts from surface water flooding. So if you took the time of that and look forwards, then on the back of that, we were able to issue tweets on the East Midlands Twitter feed, talking about slow moving thunderstorms expected, and you can see highlight this area in time. So this was done at 4:52. At this point, you can probably just about see workshop between out here. Not had a shower at this point, and Market Racing was the other location that saw flooding on that day, which again, I'd not seen a shower by the point of this initial tweet. It was very localized, but these are just a couple of tweets from impacts on both. So this is workshop at the top. You can see surface water flooding in this region, damaging several cars, various little housing estates and precincts, and likewise in Lincolnshire. But on both events, the number of properties we saw flooding was only in the tens. The area is relatively rural, not many parts of key infrastructure up in there, which meant that it was thought to remain short of an amber warning. And indeed, it was assessed by the Public Weather Service Custom Group as remaining short of an amber. However, the East Midlands Twitter feed and the reach of this work, despite all it going into the public and responders, is really small. So I've counted here the number of engagements. This is just screen grabs from Twitter that each of these tweets got. We only reached, for example, on this first one, which was the one that gave warnings so it's the flooding occurring, 527 people engaged with it. That's clicking the graphic, reading it, doing anything, and only 727 on the second one. And when you look at the people who retweet it and quote it and like it, we were unable to get any reach within the local media groups. We were unable to get anyone like the Environment Agency in the region to pass that on, police forces. And most of the people, to be honest, who engaged with it were weather enthusiasts, which were from out of area. And it basically highlights a problem that we know we have, we know we would have when we do this. We're not pushing this directly to people. It's not pinging their mobile phones. It relies on people to be monitoring these very small, poorly followed Twitter feeds to pick up on this information. And as a result, it's a lot of effort, but in terms of getting it to responders and the public, I think this year has been relatively clear that it's not cut through and it's not done a very good job. I was going to say later on in the evening here, again, my colleague was able to do this internal piece of advice where the cold front, you can see, was undercutting the cells, which meant it was a decaying or a weakening phase of convection across parts of Lincolnshire. But already this is done at 1850, able to highlight this area just around the Wash, extending southwest was down towards Peterborough, parts of southeastern Lincolnshire, Cambridgeshire. And here, for example, he was able to talk about the focus through the overnight period. So this was what was going to happen hours ahead as the cold pool moved south, convergence zone aided by frost and loft, etc. And this is where we were able to basically talk about, you know, potential for 70 to 90 millimeters to occur. And this is with actually like, you know, 4 to 6 lead times before the event happened. On the back of this, we were able to, you know, this analysis, we were able to draft up an amber warning in case it was needed. That was all prepared and left in the can, but in this case, not issued again. And it's another one really, when you talk about impacts, so our warnings are assessed on as forecasted impacts that happen and then actually being observed. It means that certainly when it's thunderstorms, you know, when it's very much hit or miss, it's almost like throwing darts at a dartboard. If you're dealing with a rural area that's sparsely populated, there is less infrastructure, less urban regions, you throw all your darts and, you know, you might need to hit treble 20 to actually cause an impact. You might need to that very small isolated town, which is the one that's susceptible. Whereas that same weather taken, for example, across southeastern England, you know, the greater London area, or parts of, for example, West Yorkshire and Lancashire, where, you know, that M62 corridor is much more heavily populated. Those same number of darts you throw at the board, you might, if you hit 20, 19 and 18, you'd have an event. And it does lead, and it does mean, certainly when we're talking about warnings, there is actually, I feel, a different level of service between rural and urban warnings, certainly when it comes to thunderstorms, you know, when it's very much that hit or miss nature. If you're in a rural area, impacts are less likely to happen. So in terms of getting an escalation to amber, I think that's more unlikely there than as if the same event was happening across the southeast. I'm almost certain that an amber would have gone out in place. So as this evolved anyway, I can show you, this is the middle one. These were 12-hour accumulations between 1800 UTC and 600 the next day. So this is valid down on the overnight period. This is derived from rainfall, and it was actually backed up by a rain gauge, which we had at Hull Beach, which recorded 115 millimeters of rainfall in only 3 hours, and resulted in some very localized, again, but surface water flooding around the town of Spalding in southeastern Lincolnshire. And that event, I say, was able to be highlighted, you know, 4 to 6 hours in advance, but covered within that broad yellow thunderstorm warning, not having the confidence or, you know, likely to hit the number of places because they just don't exist to give us those amber level impacts. No amber was issued, and no, you know, that was deemed to be quite good guidance. This was earlier in the day, so this is 12 hours up to 1800 UCC, so 12 hours previous to this period in the middle side. You could say these are the showers that impacted Worksop under this feature here, and then market raising under here again, where, you know, radar derived accumulations, there could be a little bit of hail contamination, suggested of the order, you know, 60, 80 millimeters plus, most of that falling in a few hours. But it just shows with showers, you know, that spatial scale. You know, somebody living in this middle area here where there's only blue shades would have seen barely any, you know, trace amounts of rainfall, whereas only, you know, 5-10 kilometers away, it makes that difference between seeing barely anything and having no impact, and seeing, you know, so much that it really does cause some significant flooding. And that's the difference. Does it hit the key railway line? Does it hit the key bit of motorway? Does it hit the key town or not? And that's the reason why I think, you know, rural areas are slightly done. And I'm just going to show you on the right hand side. You do know, if you remember, that thunderstorm warning covered the whole of England and Wales. I should say that there were thunderstorms that developed at other places quite widely across the country on that day at various times. You could probably see that the odd one up here in Yorkshire. And there was also an event down in Exmoor that was highlighting one of the early events when, again, 80 to 100 millilitres fell in a very small localised area, but they've been rural. No impacts were reported off the back of that, and it was judged to be pretty good guidance. So I'm just finishing up now. So the future, where do we go from here? So we're continuing to develop the capability. There's new things coming online all the time. New NWP, the new satellite, Meteosat third generation launches, you know, in the next month or two. That's got some great new capabilities, such as a lightning imager on it, as well as more high resolution, more frequent imagery across the UK, which really opens up some avenues. We've been able to see such imagery across the United States and Japan, you know, for quite some time, but yeah, really exciting changes to Europe. So we're constantly working behind the scenes to improve the Meso-Analyst capability. And we're also going to be asked to add some additional national survey warning hazards to that. So snowfall, I think, is the next one that's in the sites. But all this capability behind the scene is all good and well. But these are the main challenges really that I'll summarize as these 3 points. Who is this information? Oh, sorry, I've written that terribly. For whom can this information be useful? Can they actually use this information at a time scale, if you know, only often several hours in advance, to make better decisions more consistently that they can have trust in? And then even if that's possible, how do we get this information to them? As it doesn't sit overly well within the broader National Severe Weather Warning Scheme at the present time, which applies to big scale, big duration advisory warnings. And it makes it very difficult without small scale targeted escalations to amber, which only happen on a handful of events per year, to actually get this information through. So we need to work out this, like, if we're doing all this and it doesn't make a difference to many people, you know, I'm sure it does. And then how do we get this information out? Because regional Twitter is evidently not been overly successful this year. So I just want to thank you very much for your time this evening. Sorry, I've probably continued about 5 minutes longer than I expected. I've just added on there my thanks to the team who were involved this year. That's the 6 of us. And on the back of that, I'm happy to take any questions. And yeah, thanks once again.
Yeah, thank you, Nick. Absolutely excellent. Really informative talk. We do have a few questions, but I would just like to start off myself as somebody who first put some fired up information from a weather station when there was only a few hundred on the map. Now there's a few thousand on the map, and including Germany and the Netherlands and some of France as well. It's obviously a very popular weather site. But one of the concerns, I know you touched on it about the software the Met Office have, but bearing in mind that the WOW program is based on somebody who is firing information from a weather station that they can go online in Amazon and buy for £100. At the top end, you're buying a Davis Vantage Pro Plus for £2,500–3,000 complete. Unless these are actually maintained and calibrated properly, do they really give you the information that is helpful?
So if a weather station's inconsistent, unconsistently poor, it will be rejected. But for example, we will look at it versus official observations in the area. So for example, I'm here, I've got Exeter Airport and Dunkeswell, which are 2 sites, you know, either side of me. My weather station is bias corrected to see, am I warm, cold, you know, whatever, how do I appear to them? Through that, we're basically able to get almost like a base state of my observation and look for trends in it. So the temperature might not be quite correct, but we'll see a trend upwards or downwards, which will be picked. The pressure, which is, to be honest, one of the most frequent ones we use, which is relatively accurate and quite easy to bias correct, certainly in areas where it's flat, not too mountainous, is relatively good. So I'm not 100% sure on the whole number of algorithms that were developed to do that, but some very rigorous quality controlling and some very rigorous bias correcting. And each station only has a certain radius of influence that it shares with other local stations as well. So there are a whole host of measures in there that mean that we're confident that the density of stations for the most part is enough that they will, and the quality control, that any rubbish in there will be filtered out and not get into the analysis, and we're able to extract the value while we exclude most of the problems with it at the present time.
Okay, thank you, Nick. We have a question from Martin Young. Have you improved success of forecasting elevated instability, and do you cover the night shift when much of this can be, when much of it can erupt?
So we've had another variable summer forecasting elevated instability. The main problems remain that that area of the atmosphere, it's off the surface, it's very poorly sampled, very, very poorly sampled. So as a human in the loop trying to look for features, certainly beyond or before the point where you start to see blossoming of convective clouds and satellite imagery, it remains a challenge. And also NWP this year has had a very variable year with how it's performed with it. So as a result, success of improving elevated stability, I say not much, it's minimal, if anything, upon probably the years that Martin's talking about. In terms of night shift cover, we actually have one of our business as usual positions, which is the UK medium range, where the work between the hours that the Meso-Analyst capability is not online, 23:30 to 6 in the morning, we've actually, the work that remains in that position is actually a priority at which, if convection is ongoing, it can actually be moved, deferred or defaulted, and allow that person to provide the 24-hour cover through the night. that's probably one other area where the project's not worked well, because our specialists and where most of the training's been concentrated are in this team of 6, which are generally not the same people who are doing the business as usual night shifts. And it's meant that that area of it hasn't worked optimally through the season as well. So the Perth flooding event that I mentioned, that occurred, at the end of the night. It was initially elevated convection that formed over the North Sea, a very poorly sampled area again. We cancelled the warning, just as the event was starting. As a result, a very small area got a lot of rainfall, and that was effectively a miss or a poor performance on that thing. And that basically highlighted loads of problems. So again, elevated convection, we struggle with it. The NWP performed poorly. We didn't have the Meso-Analyst capability in. And then the overnight team as well, just by chance, human factors, I think, played into that. That meant we had 2 people who were covering sickness, which meant that elongated their shift runs. They were finishing their final shift. It was the final minutes of them, and a poor decision, with the benefit of hindsight, actually, I can say it was made in that case. So we're starting to look at it, but we've certainly not got elevated convection nailed down, and the night shift cover is something that we need to work on years going forward.
Okay, thank you, Nick. Alan MacDonald, who is one of our committee members in this, the Scottish Centre, would like to make comment on this as well. Alan, can you put your microphone and camera on if you wish to add to this one, please? No, I don't seem to be getting Alan. Okay, I'll move to the, oh no, sorry, Alan, you coming in. No, sorry, Alan, we'll come back to you on this one if you try again to make a connection. The next question was from Robert Moore. To what extent are you able to take account of possible terrain effects in the interpreting your data?
Okay, so every observation that we get, we know the height of it on terrain, and it's also gridded onto the Meso-Analyst, which does adjust for elevation of the site when it's sort of taken into account things like that. Terrain effects. So openly, so because the Meso-Analyst is going on top of model data in areas where we've got complex terrain, such as the Highlands of Scotland, and unfortunately those areas tend to be very sparse. In personal private weather station observations, they tend to be clustered around urban centres. It does mean that in many of those sparse, hilly, high areas, that it's basically a lot of model background going on, and our analysis is often done from satellite imagery and just that highballing individual ones. The Meso-Analysis tool works better where it's flat, where it's inland, so you're not near a coastline, and where you've got a greater density of observation. So in honestly, England, it has probably the best features that show up in that with the most consistency, and it's more variable and requires more interpretation across parts of Scotland. But it's just a notion of geography, where people sit. The tools we've got, the complexity of topography does add another level to that. But it is taken into account. Like I say, we adjust for station elevations. We know the height that they are, all are, and things are done in that state. So I think that's as much as I can answer on that.
Okay, thank you. Right, a question from Jonathan Smith. Does your current operational analysis influence the public web forecast? It still seems to be what must nowcast over ourselves from the radar picture. In the brackets, he's got just like today as the monitoring forecast for a dry afternoon for Edinburgh became very showery.
He's absolutely correct. Unfortunately, it has no pull through into the data, which goes out and feeds the public website and app. And there are some difficulties with that. So, for example, although on the public app it says now in inverted commas, that now is actually from a sort of a run that's gone through a computer, sometimes up to 90 minutes before that now frame is actually presented to you on the app or public website. So now, can be up to a 90-minute forecast, which means that, it can say it's a dry day, it's absolutely fine, when, there's a shower overhead, as that will take so long to filter through the system that you may have had 1 or 2 showers before it actually adjusts and changes. You'll be pleased to know, although it's still going to be purely data fed, the system that does feed the web and app is moving from something called best data, which is quite antiquated in how it works and blends data together, to a new system called Improver. And that's expected to be implemented on the web and app in the next 12 months or so. So at least at very short range, you shouldn't see that lag or so much of a lag, and it should do a better job of explaining now as actually what you see, rather than at the moment where now actually can have been effectively a forecast of an hour to 90 minutes in duration. But I'm afraid data's so big, we're unable to, we're unable to cut through in there at the present time. I can't think of a way that we can do it. So I'm afraid that it's still going to be on, if you've just got the ultimate data, just watching radar is the best thing for the meantime.
Okay, thank you, Nick. A question from Murray Dale. It's a fairly long question, but I'll just go through it. The surface water flood forecasting decision support tool developed between 2011 and 2016 involved impact as well as rainfall thresholds and used probabilistic high-resolution NWP that can give 24 to 12-hour lead time quite feasibly. This approach helps address the issues discussed of uncertainty in the impact, and also provides more useful lead times to responders. While nowcasting and new technology is excellent for understanding where rain is, responders need longer lead times to take effective action to mitigate the impact. Can you say how nowcasting can blend with longer lead time probabilistic NWP forecasts?
Yeah, I can. So I think the first thing that I will say here is that when we set up the Nowcasting project, we spoke to a whole host of responders and we asked them what did they want. And what they wanted was forecasts to a specific town at a very long lead time. And of course, we're not able to do that. I'd say the capabilities as it sits now, it varies day to day, so it's not always consistent. Some days and I must say, doing it, I know days where I think I've got a good chance of latching onto things here, giving good advice, 3, 4, sometimes even more hours in advice. Some situations I know that I will probably be struggling to less than an hour's lead time. But overall, I'd say that we're at the level where we can probably deliver information on an average case. We can highlight probably a county or a slightly area smaller than a sub-county, sometimes a lot smaller, but on average probably just smaller than a county, and probably a typical lead time is probably around about 3 hours or so. So often if you're a responder, for example, that's a fire and rescue service that's cuts across a county and want to know where to move appliances or prepare to put people in lead time, unless we just clip one part of your county with an area that we're looking at, often our advice probably won't be hugely useful to yourself. It's the whole problem, isn't it? The lead time you require, we're unable to be that specific. Unfortunately, many things it's just chaotic, and if we get the first shower of the day wrong, every subsequent one that's in MWP space or whatever can be in completely the wrong place as well. In terms of developing tools, I've worked with, I think it's called SWIFM, the Surface Water Impact Flooding model that the Flood Forecast Centre, which is the Met Office Environment Agency, and a bit of National Resource Wales partnership has put together. And that basically works on probability thresholds, looking at surface water flooding in various catchments. Again, how has it performed this year? It's so heavily NWP influenced, and NWP has biases and problems that I'd say that its performance at best has been variable as well. Different size catchments, different areas of surface water means that how it flags things is very, very different place to place. And has it given us good advice? I'd probably say it false alarms just as much as it actually picks out something that's useful. So that's going to be problematic. One thing I can say going forwards is that I've got projects on the way at the moment called Data Triage, which is aiming to develop some technology to put meteorologists in the loop of NWP, which allows us to basically put constraints on data that will feed the web and app. This is in development. I'd imagine it will take several years, probably more like the scale of 5 years till it gets through. But an example of that is where we could, for example, highlight an area, say where sites are above so much elevation during these hours. Any precipitation that the model produces, we want to turn to snow. And that may, or we hope, will have the ability to then feed through to web and app. So when you're in Northern England or the Pennines or Southern Scotland, and you're looking at a snow warning out from the Met Office, you don't see an app that's basically got rain symbols that continue. So in the long and medium range, we're looking at ways that we can actually work over the loop to help constrain the data and help, certainly in like high impact critical cases, improve the advice that will flow through directly to people through the web and app, but it's still several years away from being reality.
Okay, thank you, Nick. We have a question from Ben Maybe. How big a role does short lead time NWP ensemble output play in your decision making?
So virtually nil, I'm afraid. So Mock-Ups UK is our sort of high resolution ensemble, NWP ensemble in the UK, and we tend to see, so that has its what we call the A time, or so when it takes in observations, when it takes it and it runs. Before we see that that model pop out into our things, it's actually delayed by around about 5 hours. You know, you're running a model for multiple ensemble members across the whole UK. Well, actually, no, it's 5 hours. So that's shorter than that now. It's probably more like of the order of about 3 hours now. As a result, you know, often so much has happened in those first few hours that when you first see that that ensemble appear, you can often throw out that member just knowing that that's unrealistic, and we're not able to, not able to do anything with it. In essence, as well, our ensembles in the UK, because we try and do everything with a unified model, I think some work in the past had found that if we really bias our data assimilation towards reality now, in a longer lead time, you know, forecasting 12, 24 hours in advance, it can actually take away skill from the model. And we're trying to produce models that do a reasonable job in the short term, reasonable job in the medium term, and a reasonable job in the long term. And forcing them too heavily towards observations as there are now, although it can have some positive in the short term, can have some negative in the lead time. So effectively, we're not in that place. But I'm aware that some of the countries, for example, I think the Germans and particularly the Americans, there's a model there called WAFS, War Non-Forecast System, that is a rapidly refreshing sort of ensemble NWP model that's heavily constrained by observations. It only runs out for a small number of hours, so it doesn't, like our models, try to go to 5 days in the future or more. And that's shown some great promise forecasting convection once it has initiated. So before it's initiated, it's more variable in its results. Once it's initiated, started, it's produced some incredible things with forecasting the ratios and things like that across the states in the last couple of years. But it'd be interesting, our convection in the UK is often on a much smaller scale and not as severe, not as long-lived as that in the States. So you know, that's again one thing we're looking at, working with the Americans to port the code across and see how it could perform in the UK. But I'd imagine it'd be more limited and less or not as useful as it will in the States. But I wait to see how that evolves. But yeah, a place of investigation. But again, at the moment, they play very little role.
Thanks, Nick. Just when you mentioned about working with them in the USA, obviously in USA and Canada, they're way ahead of us with alerts. Now, your point earlier on about Twitter feed, and very few people, it's really enthusiasts who are looking at this rather than general public who are putting on their wellies to go out or putting on their gym shoes to have a nice day and then finding it's pours with rain. Is there any program within the Met Office to expand the weather alerts to people's mobile phones or weather radio like they have in the States?
Sorry, so I'll try and answer this diplomatically. It's very challenging. So the weather industry is moving more and more towards technology, you know, having to employ very skilled IT professionals. Those IT professionals are sought after by many big firms, you know, nowadays. And, you know, what UK public service is in recent years, you know, with peer restraint and things like that, means that it's very challenging for the Met Office to recruit, train and retain, you know, those people that we need in greater numbers to make these steps forwards. As a result, when we do develop things, we've you know, relied upon a lot of contractor work, which is more expensive. And it's been a very challenging set of times for the set of years for the Met Office, where effectively we're really struggling on the technological front to move forward, because we're simply finding it more and more challenging to recruit and retain the people we need to develop those tools. So we'd love to go in that direction. We have the ideas, we see what happens in other countries, you know, but we only got a very limited amount of resource, and at the moment, you know, I don't think that's one of the things that's at the top of the priority list for what we can achieve.
Okay, thank you, Nick. I think that's all the questions we have. So I'm just on behalf of the Scottish Centre of the Royal Met Society, I would like to thank you very much for your talk tonight. It's been very informative. We've had some very good questions, and we look forward to speaking with you again and hearing you again on how this updates over the years. It's a fascinating subject. and one which is going to affect us all going into the future. There's no question about that. So thank you very much indeed. Just before you go, and I'd just like to address our audience tonight. Again, thank you very much for coming along and listening to Nick Silkstone. Absolutely fascinating. And I'm sure had we done this round the table or in an auditorium, you'd all be applauding by now. So thank you very much for that. I would just mention quickly that our next talk is on Tuesday, the 8th of December, November, sorry, 8th of November this year, again at 6 o'clock till 7 o'clock. And the speaker is Mr. Neil Loney from the Dundee Satellite Station Limited, who will be giving us a history of the Dundee Satellite Receiving Station and the following on of the DSS Limited ground station. So I hope you can all join us for that. And I would thank you again for attending tonight. We had a fairly large audience tonight. It was really good. A very large audience tonight, actually. So thank you all again. And I hope you have a very good weekend. Thank you.